call it x1. No, it's not good. v1 and v2. These two are linear independent vectors that all satisfy this. So these two vectors are in the new space of A, right? And what else? Can I do a linear combination of these two vectors, and does that give me? I should stop to use A here. We call it V1, V1, V2, V2. Okay. So this will equals to what? Still, it still equals to 0. Right? So that means the linear combinations of these two vectors is also in the new space. Okay. So if you can find the basis of that new space, you can like just span the whole new space by doing the linear combinations here. And one thing that is kind of interesting here is that, okay, so we have this theorem here, although I'm not going to prove it. So let's say that in a this should be in Rn, right? So the dimension of new space here and the rank, if you plus these two together, then we will get exactly the numbers n here. Okay. So this is in the case where let me see. This is the example. Let's say that the matrix A looks like this one, and we can directly see that the third column can be is a linear combination between the first column and the second column, right? You just add these two columns together and you will get the third column. Okay. So the new space of matrix A is actually 1, and the rank of it is actually 2 because the small n is 3 here. Okay, so that's how you kind of do this kind of problem. Okay. Okay, I think I kind of remember what I tried to say in the rank here. It's kind of complicated. So I will focus on the column space here and the rank of the matrix A. Is actually is the basis, the numbers of bases. of column space. Yeah, this is something I want to say here. M times n. Right. So think of a particular case where you can directly treat n by n, or like m is greater than n. This case. Okay. If all the column vectors are linear independent, then that means all of them are the basis of column space. And that will give you the rank equals n here. If like all columns are linearly dependent. Right. In this case, n by n, or like m is larger than n. Yeah, I think that's something I want to mention in the rank sections. And if that is the case, then you immediately know that a new space of A is 0. So you can see this from how to say that, in two ways. First is that by the theorem here, like rank and nullity theorems, we know that this plus this new plus rank A will equals to n, and we already know that rank A is n, so that implies this is 0. Okay, and or you can think how to say that, you can get that answer in the following way. Now we know that our rank A is n. That means all the columns here are linear independent. And when they are all linear independent, that means the solutions of this, we don't have the unique solution of this equation, which is x equals to 0. And this since imply that new space, the nu of A is 0. Okay. Okay. We get these things because all columns of A are linearly independent. Right, so they're kind of, I don't know, like when I first learned all this stuff, they are kind of separated, but in some sense they are connected together. So you need to spend a lot of, like, a few more time to kind of think about, okay, now am I looking at in terms of linear independent, or like I can use the theorem to calculate, and now it's the new space, and now it's the column space, etc., etc. So it's kind of complicated. Okay. Right. Okay, so determined. So to calculate determinant, the object or the matrix has to be a square matrix here. okay? And we will use like det of A, or like you simply put two like straight line and between next to A to represent the determinant. Okay. And of course, like I believe like when you were in high school or something, like there's always a lot of like fancy technique to calculate the determinant, right? But here, I'm going to teach you like the easiest way, and kind of like troublesome. Now it's like going to be time consuming, but you're not going to make a mistake here, okay? So we are going to do the row operations, which means that you can do one row multiplied by some numbers and then like add it up to another vectors. So I'm going to show you here.